Okay, welcome to lecture here. We'll get started here in just a second. Just a reminder, if you could type here in the chat box for roll, I'd appreciate it. And again, we're continuing on with chapter 2, and then I believe we should roll into some chapter 3 after that. Or, I'm sorry, chapter 1, then roll into chapter 2. That would probably be better, I guess. Okay, so we've been talking about conversions, conversion factors, performing really dimensional analysis is what it's called. And it's really when you do your calculations, you want to do it in a way where you can see the units, canceling out, you can see which units do not cancel out. And again, it's a system really of using conversion factors. And again, the idea there is to cancel out the units you don't want and end up with the units that you are looking for. And it's basically opposites will do that for you. So things in the opposite sort of location in terms of units will cancel each other out. And again, if the unit on the bottom is what you want to cancel, you need to put the same unit on top. If the unit's on top, then you need to put the same unit on the bottom to cancel it out as well. All right, so I think where we left off was here on this particular, excuse me, on this particular example here. So why don't we go through it? So here we were going to be traveling 125 miles, and we're traveling at 55 feet per minute. And we're going to basically use that to figure out how long it's going to take us to basically go that distance. So the 55 feet per minute can also be used really as a conversion factor. And you could use it in that form, or you can use it like other conversion factors. You could put the minutes on top if you needed to, and the 55 feet on the bottom as sort of a conversion factor in that sense. So what we're looking for here is we need this conversion and our distance, which is 125 miles, to basically turn it into time. Since that's what we're looking for, we're looking to basically figure out how much time it is. We do have a little bit of an issue on this particular one because the unit of length here is in feet on this one, or distance. And the unit for kind of length or distance is miles on this one. So as it stands now, we really can't use them together because the units will not cancel out correctly. So we do need to do a conversion. You can either convert the miles into feet, you could convert the feet into miles, whichever way that you want to do that will work. I'm personally going to convert the miles into feet. So the first conversion I'm going to do is going to use this equality that we talked about last time, that there are 5,280 feet in a mile. So I'm going to take my 125 miles, which is basically my distance. I am going to use that conversion. Again, opposites in terms of the units. So 1 mile on the bottom and 5,280 feet on top. As we talked about last time, essentially we're going to be dividing miles by miles. So they will cancel each other out. And if I do that really quick here, I get 125 times 5,280. Again, multiplying across the top and dividing by the bottom gives me something like 660,000 feet in this case. And again, the purpose of doing this conversion is so that we can actually use this guy that they gave us. Again, now we're both in feet and feet, so they should cancel each other out. So if I take my 660,000 feet, now I could use my rate that was given to me. And again, I'm going to want to use the feet actually at the bottom here so that they do cancel. And that conversion right there, by using the rate that was given to us, is going to allow us to really go from distance to time, which is ultimately what we're looking for here, right? Because we want to figure out how many days. Here again, the feet are going to cancel. If I stop right at this moment, I am in units of minutes, which is close to what I want, but I do want to know days. So I do need to now do a couple conversions perhaps to get me to days. Again, here going opposite in terms of the units. Minutes are on top, so I do know that there are 60 minutes in 1 hour. Again, opposite location for those units so that they cancel. If I stop the calculation right at this point, I am in units of hours, which is close to what I want, but again, I need to get into days. So obviously, hopefully we know there are 24 hours in a day. So we will use that as our last conversion here of 24 hours in a day. Again, we want to go opposite, which is hours on the bottom. So we're going to put our hours on the bottom here so that the hours cancel. And days will go up on top. Again, hours in opposite locations are going to cancel each other out, just like you basically divided them. So math-wise, like we talked about, you're basically going to multiply everything you got going on up on top, and then I would hit equals. And then we're going to come back and divide by everything on the bottom. Again, here I would divide by the first number, hit equals, divide by the next number, hit equals, and then you should be okay. Divide by the last number and hit equals. Again, I think as I maybe mentioned last time, sometimes people try to put everything in all at once. And as they put everything in all at once, if they don't put parentheses in the right spots or anything like that, sometimes it will do a weird calculation. So we'll go with 660,000. We're going to basically divide it by 55, hit equals, divide it by 60, hit equals, and divide it by 24 and hit equals. And we will end up walking for about 8.33 days. That's a lot of walking, yes. Any questions on any part of that calculation there? In terms of significant figures, the only two numbers really given to us here in this problem, and since all we really did was multiply or divide, everybody here is essentially 3 significant figures. So that's why I took the answer there to 3 significant figures at the very end. Any questions on that? Yeah, so again, in terms of sig figs, in this particular case, you would probably want to go with 3 because of this. Number here is 3, this number here is 3. So really the smallest number of sig figs on the numbers that were given to you are really 3. It technically should be 3 there when it's all said and done. Would you get it completely wrong? Probably not. It is sort of sig fig wrong in that sense. If you did, the question is, if you just put 8.3, would it technically be wrong? And again, just in the aspect of sig figs, it would be wrong. Calculation wise, it would be, correct in that sense. Other questions on that? Yeah, so that sometimes happens if you do get a fraction on your calculator. So let me see what I could do here. You usually have a button. Let me see if I can find what that button looks like. Sometimes I think the button, I'm trying to remember, I think sometimes the button may even have like an S and an arrow to a D or something like that. My particular one has like a button that looks something like, actually like a couple of arrows like that and like a kind of equal sign. So usually you'll have a button somewhere on your calculator that will turn the fraction into a decimal, which you definitely want to do. Other questions on that? Okay, any questions on conversion type problems here? Okay. All right, so the next thing we're going to do, and that's a good question actually, because again, sometimes a lot of people have that happen on their calculator. So there usually is a button on there somewhere that will kind of turn it into a decimal and stuff like that. We'll do some extra practice and stuff like that. We'll have some worksheets where you could do a couple more of those, but we do need to kind of continue on. So let's talk about density here next. So density really is the property tells us whether or not, for example, something will sink or swim. Sink or swim? No, I guess that's the wrong word. Sink or float, I guess, is the better way of saying that. If, for example, water, if something is more dense than water, what will happen is it will sink. If something is less dense than water, it will typically float in that water. And density is really the amount of matter mass there is per volume of solution. And when we look at the density, there is an equation that goes with it, and it is D is equal to M over V. D is density, M is mass, and V is volume. And the common units that we see for density are these guys down here. This one really should be grams per cubic centimeter. The 3 should be higher. Are grams per milliliter. And these are the common units that we see for solids and liquids. And honestly, in our class, these are probably the common units of density that you will see. If you ever take another chemistry class down the road, maybe, or something like that, if you talk about gases and you talk about sort of density, sometimes gases are given in terms of density and grams per liter. But again, probably in our class here, you'll probably only see those kind of couple of units. Also, another really important thing to remember is that those are essentially the same thing. And what I mean by that is a milliliter is the same thing as a cubic centimeter. So it's a 1-to-1 relationship. So if you say the density is 4 grams per milliliter, it would also be 4 grams per cubic centimeter. Again, it's a 1-to-1 relationship in terms of cubic centimeters and milliliters. The density of water, for all intents purposes, if you're ever asked, what is the density of water, or, you need to use the density of water. Typically, the density of water is considered to be 1 gram per milliliter. I will tell you the truth that density does change with temperature. So as the temperature changes, so does the density of a substance. And for water, its greatest density is about 1 gram per milliliter. At about 4 degrees Celsius is about where that occurs. And pretty much, like I said, if somebody says, hey, what is the density of water? That's usually the number they're looking for. But a little side note to that is, again, it does change with temperature. When we think about density here, this formula here, you do need to be able to rearrange. So you need to be able to solve for any of those things. If we bring volume to the other side, volume would equal mass divided by density. Also, if we wanted to solve for mass, it would be volume times density. Here we're multiplying the volume to both sides. And in case of the volume, we're multiplying the volume and coming back and dividing by the density. Now, sometimes people will remember this by the DMV. Everybody loves the DMV here, the DMV triangle. So you got a nice little DMV triangle going on. Density is mass divided by volume. Volume is mass divided by density. And mass is density times volume. So sometimes that's an easy way to sort of remember how to sort of properly rearrange these guys. And again, you do need to be able to solve for any one of those 3 things if you're given the other 2. And so you're oftentimes asked to solve for density, mass, and volume. This is also something kind of interesting, right? So if you took like a Diet Coke or Diet 7-Up in this case, and a regular Coke or a regular 7-Up, and you toss them both into some water, you may assume that they both might have sunk. And as you can see in this picture, that's actually not the case. Only the regular soda there sinks to the bottom. The Diet soda actually floats. And one of the reasons for that is in a regular soda, there is a lot of sugar, right? So all that sugar basically weighs it down, makes it heavier, and it actually sinks. While in diet soda or diet Coke or whatever it may be, it is artificial sweetener, which you don't have to put as much in, doesn't make it as heavy, and it actually will float, which is kind of interesting. Another interesting sort of aspect of things, especially water, for example. Water is an interesting sort of substance. The density of ice is actually less than the density of liquid water. And we know that in just real life because if you put ice in your drink, it usually ends up on top, right? It floats rather than sinks to the bottom. So the density of ice is actually less dense, or density of solid water is less dense than liquid water, which is a very unusual property. And that's really because when water comes together in the solid phase, I'll just draw it like this, it creates a lot of really open area between the different water molecules when they come together in the solid space. And if you think about density, which is mass divided by volume, by having all that empty space is making the volume part here a larger number, which means the density will become a smaller number. If you take a small number divided by a large number, you end up with a smaller number. So that's an unusual property. Most things are much more dense in a solid state than its liquid state. Here's a table from your book, again, of some common densities of things. And again, water, there are 4 degrees Celsius, has a density of 1 gram per milliliter. So everything less than that is less dense in it, and you would expect to sort of float in it. Anything higher than that would sort of sink, like obviously bone and stuff like that would be much more dense. All right, why don't you try one here? A block has a volume of 25.3 cubic centimeters. Its mass is 21.7. What is the density? So take a second here and calculate it. Okay, so on this particular one, I see some answers rolling in, so that's looking good. So let's take a look and see. So in this particular one, we do have the mass given to us, and we do have the volume. So the mass here is 21.7 grams. Volume is 25.3 cubic centimeters. So basically, density is mass divided by volume. So we pretty much have both of those things. So putting in our mass of 21.7 divided by our volume of 25.3. And when you do that, you do get 0.857770751 on the calculator. Units are grams per cubic centimeter, as they do not cancel, so they both remain. Now I see a little bit of variance in terms of sig figs there coming through on the chat. So let's talk about sig figs. Here we are dividing, so that is 3 significant figures. Here is also 3 significant figures on the bottom. So remember, when we divide, we are looking at significant figures. So we should end up right about there in terms of significant figures. And because the next number is a 7, it should round, like I see some of the answers there, 0.858 grams per cubic centimeter there, as I scribble that bad 3. Question on that calculation. So that's very good. I see some good answers in there. All right, I think we've got another one perhaps. No, let's talk a little bit about another aspect of density and really volume part of it. So we've talked a little bit about kind of 2 different ways that you could kind of get a volume. One way you could get a volume is pretty simple. You just, put the liquid in a container that has a scale, and you could take a reading. We always read a liquid from the bottom of the meniscus. That's the part that curves when you put a liquid in a glass container. And that's one way you could get it. You could also get it by doing some measurements. If you take the length times the width times the height, and again, each of these are measured in centimeters. That will give you your cubic centimeters, which again is a volume. Now, a third very common way to get a volume is what is known as volume by displacement, and especially comes about when we talk about density. And basically the idea here is if you put a solid object in a liquid like water, it will displace a volume that's equal to its own volume. So for example, before she dives into this pool, there is an initial volume of where it's at. After she goes in, she's going to displace the water. It's going to rise. I saw the hands go up, so yes, it will rise. So, and we will have a final volume that will happen. And really the difference in those water levels, if I could draw a straight line on this, you get the idea, almost straight there. The difference between sort of where it started and where it ended is the volume of her in this case, or the object. So the volume of the object when you do something that is volume by displacement is equal to the final volume minus the initial volume. So when you put that solid object into that liquid like water, it will make the water rise. And again, the difference from where it started to where it ends will equal the volume of the object that you put in there. And that's a very common way in density that people do get the volume. So why don't you try one here and see what you come up with. A student fills a graduated cylinder, which is that glass cylinder that holds water, and you can measure water with, or liquids with, 25 milliliters, then puts a solid in the liquid. The volume goes to 33.9. If the mass of the solid is 63.5, what is the density? So take a couple of minutes and pop in your answer there in the chat if you like, kind of see how we're doing, and then we'll come over it. Okay, so let's take a look and see some answers rolling in. So that's good. So let's kind of visually kind of think about what's actually happening here. So again, a graduated cylinder is basically a cylinder here where we put liquid in. So when we start, we have an initial volume of 25 milliliters. Then we have this solid that has a mass of 63. We're going to drop it in there. And then what will happen is our graduated cylinder will get wider. I'm not sure how that happened. The liquid should go up, right, when we put that in there. And again here, this would be our initial volume. This would be our final volume. So it does go to 33.9 milliliters. So the first thing we want to find is the volume. So the volume of our object here, again, would be our final minus our initial. So we're going to take 33.9 minus 25.0 milliliters. That's going to give us 8.9 milliliters. Remember that again, density is our mass divided by volume in this case. So now we do have the volume and we were given the mass, so we can plug it into our density, and that would give us 63.5 grams divided by 8.9 milliliters. And I agree with almost everybody I see in there, 7.1 grams per milliliter in this particular case. So in terms of significant figures, it is really based off of this calculation that we did here. When we did this calculation, we are subtracting, which means we want to go to decimal places, and it is 1 decimal place on both, which means our answer did go to 1 decimal place, which is correct. But this number with 1 decimal place does have 2 significant figures, and that plays a really important role when we do the last part of the calculation here. This is 2 significant figures. This is 3 significant figures. And the last calculation we're doing is dividing, where we look at significant figures. And that's why we do round it up here, around it to 7.1, which is our 2 significant figures in this case. Again, the number stays with the grams, and it is per 1 milliliter. Any questions on that particular one there? Okay. Again, if you do have questions, feel free to ask, and we'll go off to the next one here and give you one more to go at. And again, kind of like the last question as well, it's not wrong in the sense of the calculation part that you did. If you did answer 7.13, it is wrong in the sense of significant figures, because it should be 7.1. So you technically should give everything the right number of significant figures, especially in these early chapters, and past them as well. But these early chapters, which sort of devotes itself to significant figures, you definitely want to try to get the right one. So again, you wouldn't be zeroed out on an answer like that. You might be dinged on significant figures, but you do want to try to get the right sig figs. All right, so give this one a go here. We have 150 cubic centimeters of salt. Density is 2.16. How many 1 pound boxes? And 1 pound is 453.6 grams. Okay, let's take a look at this. So here are a couple of things. If you're not really sure sort of where to start, perhaps, you sometimes want to pull out the information from the problem So 150 cubic centimeters is a volume. So we definitely have a volume going on here. We obviously also have the density, which is 2.16 grams per cubic centimeters. So obviously it does something with density. So if you weren't sure really where to go with this problem, you do have the density given to you, you do have the volume. So it would really make sense to sort of get the mass of it. And to get the mass, it would be volume times density. We could really use our density as a conversion factor. We could use it like that. We could also flip it the other way if we needed to, with the cubic centimeters on top to 2.16 on the bottom. So if we start with our volume, which is 150 cubic centimeters, using our density really as a conversion factor as well, 2.16 grams on top, cubic centimeters on the bottom, opposites so that they cancel. That gets us 324 grams of salt is needed. And in this particular case, in terms of sig figs, this is 3. And this guy is 3, which means 3 would be okay here. But it is important to make sure you do answer the actual question, which is how many 1-pound boxes of salt would you need? And really the answer is you just need 1, really, right? 1-pound box. As 1 pound is 453 grams or so, 454 grams. So you got over 100 grams of spare salt, just in case you need it for something else or you mess up. And I see some answers in there, and that would be actually how many pounds of salt you need. And that would be the correct answer, 0.714. If it asks specifically how many pounds of salt, pounds of salt that you need in that particular case. So 1 box would work. 0.715 is fine. That's actually the correct number for how many actual pounds of salt you need. But you do want to always make sure that you do answer what the question asks. Any questions on density, how to calculate density? Again, you need to be able to calculate any of those 3 things: density, mass, volume. Also figure out the volume in several different ways, taking a reading, length times width times height, and volume by displacement. Any questions on any of that there? Okay, if I'm not mistaken, that should be chapter. No, it's not. I am mistaken. All right, we're almost there. So last thing we're going to talk about in this chapter is temperature. And there's 3 different temperature scales that we commonly come across. One is degrees Fahrenheit, where we have our freezing at 32 degrees Fahrenheit, our boiling at 212 degrees Fahrenheit. Degrees Celsius, where we freeze at 0 degrees and boil at 100 degrees Celsius. And Kelvin, which is probably a new temperature scale for most of you. And it used to be called the absolute temperature scale, later named after a guy named Kelvin. And one major thing one major difference between these 2 things is these as degrees Fahrenheit, degrees Celsius. But for Kelvin, we do not use the degrees. We just use a capital K. So it's just Kelvin. So you would say, hey, I have 298 Kelvin, not 298 degrees Kelvin. So it's just straight Kelvin when you do that. The real differences between the freezing point and the boiling point here, as you can see, is 100 for these guys, about 180 for that guy there on Fahrenheit. That really is how we get our conversions between the different temperature scales. And here are the formulas that you should know. To do Celsius to Kelvin, which is probably in chemistry the one that you definitely will do the most. Pretty much every formula that we use requires the temperature to be in Kelvin. And if it's not in Kelvin already, it probably is in Celsius. So it's pretty simple. Temperature in Kelvin equals temperature in Celsius plus 273. The correct answer number is really 273.15. If you want to use the 0.15, you can. Probably 9 times out of 10, people really don't use the 0.15 because it gets rounded off in most cases along the way. But if you want to use the 0.15, don't have a problem with it. I personally will just use 273 on this conversion. Also means occasionally you need to go the other way. So the temperature in Celsius would be the temperature in Kelvin minus 273. So again, this part right here is something that you do a lot in chemistry, that conversion. Going from Celsius to Fahrenheit, the temperature in Fahrenheit equals 1.8 to temperature in Celsius plus a 32. And to get to Celsius from Fahrenheit, you bring the 32 to the other side and divide by 1.8. And that is the temperature in Fahrenheit minus 32 divided by 1.8. That 1.8 number is that difference between freezing and boiling points on those scales. And really that 1.8 is also the same thing as perhaps a fraction that you learned maybe a long time ago as well. You'll sometimes see people use that 9/5 fraction, which if you take 9 divided by 5 in your calculator, you will get 1.8. So again, you could use the fraction part of it if you like in that particular case. I would say probably outside of this chapter, you probably won't be doing a heck of a lot of these conversions. You mainly will be doing this conversion up here. If you did have Fahrenheit and wanted to go all the way to Kelvin, you got to take it from Fahrenheit to Celsius and then Celsius to Kelvin in that particular case as you go through it. Now, let's talk a little bit about sort of significant figures and temperature conversions. And the rules that people generally follow with significant figures and temperature conversions is a little bit different than our normal sort of significant figure rules. And this again applies only strictly to temperature conversions. So if you do basically a conversion of a temperature, and that is all you're doing is changing it from, say, Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin. The general rule is you make the answer or the converted value look like the original value. And again, this is strictly for temperature type conversions. What I mean by that is if your original value went to, say, the first decimal place, you would then convert the temperature you're doing to 1 decimal place. If the original value that you are converting in terms of temperature was a whole number, when you do the conversion, you would convert it to a whole number as well. So it is really kind of different. And the reason it's different is really this part of it. As you can see here, I use 1.80. When I write it myself, I sometimes just use 1.8. Sometimes people use the fraction 9/5. So there's a lot of variation that could happen if you try to do really strict significant figures on temperature conversions. So this is really sort of the general rule that everybody follows. Whatever that original number looks like, and if you're doing nothing else with it other than taking it from one temperature scale to the next, you just make the converted value look exactly like the original one. So again, if it went to 2 decimal places, the original value, when you convert it, you should take it to 2 decimal places as well. Question on that there. So we do have some examples, so why don't you take a few minutes and work those out. First one, we're going Celsius to Kelvin. Second one, Celsius to Fahrenheit. And last one, Fahrenheit to Celsius. So see what you come up with, and we'll talk about it in a couple minutes here. Okay, so let's take a look, see how we're doing. Let's see some answers flowing through. It's looking good. So the first one here, we are going from Celsius to Kelvin. So that is a most common conversion. And again, the temperature in Kelvin here would be our temperature in Celsius plus a 273 to that. And if you do that, I believe you are correct up there. You do end up with 301.5 on a 28.5 plus a 273 gives you 301.5. Again, here would just be capital K, Kelvin, no degrees or anything like that for Kelvin. And again, here, original value, 1 decimal place, converted value, also 1 decimal place. So again, for temperature conversion, that is what you're looking at. Here we're going from Celsius to Fahrenheit. So the temperature in Fahrenheit is 1.8, the temperature in Celsius plus a 32. That means that we go 1.8 times 41 plus 32. And if you do that, you do end up with 105.8 degrees Fahrenheit. Is this the right answer in terms of sig figs, though? When we look at our original number here is a whole number, which means we actually should round this to a whole number, and we should actually take this to 106 degrees Fahrenheit. Again, remember that when you do conversions on temperature, you want to make the converted number look just like the original number here. So again, we do want to take this one and actually round it to a whole number so that it looks just like the original number. So that's why we would round this one to 106. Again, the 8 that's next to it means we should round up in this particular case. Last one here is Fahrenheit to Celsius. So we're going temperature in Celsius is our temperature in Fahrenheit minus a 32 divided by 1.8. So for the first one, I assume you're talking about this one here, yeah, where we went to Kelvin. Yeah, so when we went to Kelvin, so the question was on the first one here, you know, again, why did we do that? We did it because the original value here went to the first decimal place. So when we converted it, we would also keep it to the first decimal place, just like our second value here was a whole number. So we need to kind of get it to a whole number in this particular case. So remember that the temperature doesn't necessarily have to always be a whole number, but what it does have to do when you do a conversion is it has to look just like it did before you converted it in terms of how many decimal places you took or whatever it may be. Other questions on those there? Okay. If the next question, are you talking about this one here? If we rounded to 110 on that one? If we rounded to 110 on that one, it technically would be wrong because that's an incorrect way of rounding. So since we wanted to end right here on the ones place, we would look at the one next to it and just round the ones place. When you would round up here, you would actually be taking it way too far because we really shouldn't end up here. We should end up at the whole number, which is where the 5 is in that case. So technically 110 would be wrong in that case, wrong in the sense of not the correct way to round it in that sense. Other questions on that? And it kind of goes back to what we were talking, I think, the other day as well. You do want to sort of avoid super rounding and stuff like that, that it kind of changes the meaning of the value. So when we round to 106, that is essentially the same thing as like 105.8. When we round to 110, you've now jumped up, you know, over almost 5 degrees in terms of your rounding of where the actual value is. And it's more of a disagreement in terms of the rounding than the actual calculation. So you're kind of making the number worse by rounding sort of incorrectly in that case. In this case, on the bottom here, we would take 160 minus 32 divided by 1.8. And in this case, we do get 71.1111, whole bunch of ones, I think, on my calculator. And that would be degrees Celsius. So here we want to again look at our original number. And remember, not strictly like sig fig sort of rules. It's just making it look like the original number. Original number here, again, a whole number. And to get to a whole number, that is right here at the first one. And we would round this to, as I just scribble over, let's go this way. And we go that way. Maybe we'll try to 71. Let me get an eraser. I'm just like drawing art all over this. Let's try this again here. Get rid of that. Get rid of that. All right. Take 32. Here we go. That's why they invented erasers. So let's go with 71 degrees Celsius. There we go. So it should round to 71 degrees Celsius. Again, whole number in this case. So remember, to get us to a whole number in the second one and the third one, we really just need to stop at the ones place. So we want to do the correct sort of rounding. In that case, we would look at the next one over, and we would just drop off all those guys because it's less than 5. Question on temperature conversions and sort of significant figures involving temperature. Again, slightly different than the sort of strict rules that we have when we're doing calculations. And again, this is sort of the commonly used one in terms of temperature. They really don't apply. So that's exactly what I was actually just saying. The normal significant figure rules really don't apply to temperature conversions. Again, if all you are doing is simply taking a number from one temperature scale to the next. And again, the real reason for that is, like I was mentioning earlier, some people use 1.8, some people use 1.80, some people use the fraction. So if you really try to follow those strict rules in terms of significant figures, everybody will come up with a slightly different answer. So usually people follow this general rule here for just temperature conversion, where it's a very simple one. Whatever the original number look like, make the converted number look like, in terms of how far it goes, how many decimal places, or if it's a whole number. Other questions on temperature conversions? Obviously, you do need to be able to do these temperature conversions. They probably will not be provided for you, so you do need to know how to actually do those calculations. And like I said, outside of probably chapter 1, this is really the one that you will super use the most throughout chemistry, which is going from Celsius to Kelvin. Any questions on any of that there? Now I think perhaps we are at the end of chapter 1. So we are going to then roll into chapter 2. Just give me a second here to get that going. Okay, let me do this. Let's do that. Let's do this. Let's do that. Click a little there, maybe. Do a little bit of that. And a little bit of that as well. And should be off here to chapter 2, I think. All right. And if somebody just wants to let me know or type into the chat box, looks okay on your screen. It's the right size, not super small or anything like that. Again, on my screen, everything kind of always looks the same, but sometimes it doesn't translate very good. Okay, perfect. So we're off to chapter 2, which is atomic structure. And in this chapter, there's a lot going on in this chapter. We're going to talk about the atom. We're going to talk about different parts of the atom. We're going to talk about protons, electrons, neutrons. We will also talk about the periodic table, I believe, in this chapter. And we will finish up sort of talking about, if I'm not mistaken as well, electrons, electron configuration. So there's a lot of sort of information in this chapter. And so we want to make sure we keep up with all this. So let us go with starting to talk about it. So first off, though, let's talk about some common elements and their symbols. So, again, this is normally where I point to the periodic table. So look at the periodic table in your book, perhaps. But on the periodic table is all of our elements and a couple of things about the symbols, which I think we might have touched upon maybe there in chapter 1 at the very beginning. But when we do write symbols, it's really important that we do write them correctly. And there's really two ways the symbols are written. You can kind of see them in some of these examples. If it is a two-letter symbol, which is very common, the first letter is capitalized. The second is not capitalized. If it is a one-letter symbol, it is always capitalized. So that's really important to remember. And I think I might have even done this example with you, but again, if you wrote capital C, capital O, that's actually carbon monoxide, which is very different than capital C, lowercase o, which is cobalt, which is an element. So again, if you are writing symbols, you shouldn't capitalize everything because you may be writing something that you're not intending by doing so. Now, some symbols go with where things were discovered by the scientists that discovered it. So some things have some interesting sort of symbols and names. Some common ones that we see a lot. Na is sodium, right? K is potassium, as we see. Fe is iron. That's another one. Pb is lead. Sn is tin. That's a common one. Se, my favorite, is selenium. So there's a lot of symbols. And again, sometimes we may not be familiar with those, but we do need to get sort of familiarity with it. Ag is silver. Au is gold. Hg is mercury. So as I might have mentioned earlier, but just to sort of mention it, it's a really good idea for you to start getting some familiarity with the element names and the symbols that go with it. Because very shortly, I think perhaps maybe in the next chapter, we will start talking about naming things and nomenclature. So it just makes your life a lot easier if you have a very good understanding of the symbols and the elements that go with it. Because there's a lot of rules that you have to follow as you go about naming things. And if you're really struggling with naming and the symbols, it makes it a lot harder. So here's some of the symbols. Here's some of the rest of them as well, with some unusual sort of symbols and sort of the roots of those names. And again, I might have mentioned it as well, but if you look at the periodic table, we do hit a lot of the elements in the first couple of columns. The end part over here, sort of this part of it, a little bit here. Not too much in terms of down on the bottom, maybe uranium. But usually if you think about periodic table, kind of left side, right side, upper right side, and kind of in the middle of the periodic table. And then there's kind of a patch of guys like right about there where tin is, where lead is in that case on the periodic table. That you should really kind of know these symbols. As we go through these couple of chapters or so, you'll get pretty good handle on probably the symbols and stuff that you should know and the elements that you should know as well. So let's talk a little bit about the atom and the structure of the atom. And the atom is really the basic unit of any element that there is. Atoms, although they're extremely small, there's a lot of experiments that were done that basically discovered that although they're extremely small, they do contain even smaller particles. And those smaller particles are what are referred to as subatomic particles. And there are three such subatomic particles. There's electrons, protons, and neutrons. Electrons are negatively charged. Protons are positively charged. And neutrons basically have no charge. And there was a lot of sort of experiments that were done, and there was really a very big experiment that was done, which is referred to as the gold foil experiment. And basically what the gold foil experiment pretty much did is they shot what are referred to as alpha particles at pieces of gold foil. Alpha particles are positively charged radioactive particles. And basically by doing these experiments, they were really able to investigate, sort of the structure of atoms. And they were actually really surprised at their outcome. An earlier model of the atom, was one where electrons were sort of embedded inside. There's all this positive charge all around. And the gold foil experiment really disproved this part of the atom, or this model of the atom, which was sometimes referred to as the plum pudding model. And it basically disproved this model as being correct. And what they ended up having to do was come up with an idea of an atom. And basically, as a result of Rutherford's experiment, his gold foil experiment, they said that the atom is mostly empty space. It is made up of a positive core, which is known as a nucleus. And electrons are flying about the nucleus at some distance. So there was a lot of experiments that happened from Rutherford on. And basically the idea was, in this nucleus, we had two types of particles. There's the proton and the neutrons are found in the nucleus. So these two guys right here are found in the actual nucleus. So this is our nucleus. We have our protons, which are positively charged. We have our neutrons, which have no charge in it. And our electrons are basically out and about flying around. One important note about electrons do not fly in pretty circles. They really don't fly in pretty circles. Electrons actually fly, pretty randomly about the nucleus. They do not move in a nice circular path or anything like that. So usually very common in biology. They kind of think about it in a circle path and stuff like that. Electrons actually don't travel in that way, but they are out from the nucleus at some point. In terms of the masses of these different parts of the atom, the proton has a mass of 1.6726 times 10 to the minus 24 grams. The neutron has a mass of 1.6749 times 10 to the minus 24 grams. And what that means is the neutron is actually the heaviest of all of the particles. So the neutron is the heaviest. The proton is the next, and actually the electron is the lightest out of all three of those particles, with a mass of 9.1 times 10 to the minus 28 grams. And what they said was most of the mass of the atom is the nucleus. And that makes sense because inside the nucleus, you have protons and you also have neutrons. And each of those individually, a proton and a neutron, is about 1,800 times heavier than an electron. So most of the mass of the atom is made up of that nucleus, which has our protons and our neutrons, with our neutrons being the heaviest, our protons being the next heaviest, and our electrons being super small. Now, there's a very important concept in chemistry, which is the idea of electrostatic attraction, which is a fancy way of saying opposites attract, yeah? Just like in life. Just like in life, you get two positive people near each other. I'm not sure they want to be near each other, right? Too cheerful. Get two negative people near each other. Not so good either. But, you get a positive person, a negative person. They sort of balance each other out, right? And it's the same thing in sort of chemistry as well. Things that have opposite charges are attracted to each other. Things that have the same charge, they don't like to be near each other, so they repel. So when we think about the atom itself, inside the atom, we have these protons and we have these electrons which are flying about. So there is some attraction between those electrons which are flying around the nucleus in a random motion and the actual nucleus itself. And as we'll talk about in some later chapters, this is why certain electrons are involved in things like bonding and other electrons are not involved in bonding. Those electrons that are closer to the nucleus, they're going to be held much, much tighter because that positive negative attraction going to hold them together. Those that are flying out way away from the nucleus are not going to feel as much of an attraction. They're not going to be held as tightly. And they are typically the ones that are involved in things like bonding when we do get into bonding. So you need to know the structure of an atom. An atom, again, is mostly empty space. It has a nucleus. In the nucleus is where we find our protons, which are positively charged, our neutrons, which have no charge. The neutron is the heaviest of those three particles, followed very, very closely by a proton. And our electrons are flying around the nucleus at some distance, again, in a random sort of pattern. And they are about 1,800 times lighter than a proton or a neutron in terms of their mass. And that's what's sort of represented here. I don't know how much is picking up, kind of this bluish sort of area here that is sometimes referred to as the electron cloud. That's the area where these electrons are basically flying around. And again, it may be really hard to pick up maybe on your side, I don't know, or maybe it's not that hard. But if you look where the nucleus is, it's much more blue in this area, which shows there's a greater chance of finding electrons near the nucleus. And if you kind of look at the picture, it gets lighter blue as you kind of go away from the nucleus, which means, there's probably a lower probability of finding electrons out in that area. Any questions on sort of the structure of the atom? You don't have to worry too much about Rutherford's experiment or anything like that, but you do need to know, again, the basic structure of the atom. You need to know that a proton is positively charged. You know a neutron has no charge. You know an electron is negatively charged. You also need to know that a neutron is the heaviest of those three, followed by the proton, and the lightest being the electron. And lastly, you need to know where in the atom you would find all those three things: the proton, the neutron, and the electron. Any questions on any of that there? Okay, so then let's talk about some aspects here of an atom. And we're going to talk now about atomic number, mass number, and isotopes and what each of those things mean. And I think we're going to start with atomic number. The nice thing about really sort of chemical reactions and basic chemical reactions is pretty much most of the chemistry is involved with the electrons. And we just think about sort of the model of the atom that we've just been talking about. On the outside of the atom, essentially flying around, are our electrons. And that would make sense that when one atom comes together with another atom, they are really the first ones to come together and say hello to each other, right? Is those electrons coming in contact. And it's the basis of bonding, as we'll talk about in later chapters. It's really what happens in chemical reactions. Electrons sort of break apart their bonds, they make new bonds, and new stuff is formed. So the first important sort of number that we're going to talk about is the atomic number. And the atomic number is sometimes abbreviated with a Z. And the actual definition of the atomic number is it tells you the number of protons there are in the nucleus of an atom. Now, if an atom is neutral, which means it has no overall charge, if you think about the three types of particles we've just been talking about, protons are positively charged, electrons are negatively charged and neutrons have no charge. So if the number of protons are positively charged and it's neutral, you would have to have the exact same number of electrons. So if you are talking about a neutral atom, the atomic number, which is the number of protons, will also tell you the number of electrons there are in that particular atom. And if you look at the periodic table, you can actually find the atomic number on the periodic table. So when you look at the periodic table, you got something like hydrogen. You have 1 written above hydrogen, and you also have 1.008 usually written. This number that typically is written above the symbols on the periodic table, that is the atomic number. And if you happen to have a periodic table near you and you look at the periodic table, what you will see is there is absolutely no number that repeats on top. All of these elements, every individual element has its own atomic number. There is no repeating happening. What that really means is you can identify what element you are talking about if you know the atomic number, and by default means you know the number of protons. So for example, if you look on the periodic table for nitrogen, what you will see is something like 7, an N, and 14.01 probably. This again is the atomic number for nitrogen, which means if you had a neutral nitrogen atom, the number of protons would be 7. So he would have 7 protons, which are positively charged. And because it is neutral, he would also have 7 electrons. 7 positives and 7 negatives give you a 0 overall in terms of the charge. But it is very important to remember that the actual definition of atomic number is only the number of protons. So although it does tell you the number of electrons if it's neutral, if somebody asks you what is the definition of atomic number, your answer should be it is only the number of protons that are found in the nucleus of an atom. Again, it doesn't mean the actual electrons. So atomic number really important. It identifies what element you're talking about. And since the atomic number doesn't repeat, in terms of identity of elements, the most important factor in terms of protons, electrons, and neutrons is the protons, as that is what tells you the actual element that you are talking about. Just like hydrogen there, hydrogen would have 1 proton that's positive and 1 electron that's negative. It would be, we're actually, when we kind of get done with this little section or towards the end of this little part we're talking about now, we'll talk about what happens when things do have charges. Unless it's indicated that it has a charge, and typically you could see a charge. If you look at the symbol, charges are usually written upper right of the symbol. So if you do not see anything there, or it's not specified that it has a charge, it's probably safe to assume that it is neutral. And we'll talk about at the end here what happens when things do get charges and what to do in that situation. But other than that, you could usually assume that it's neutral unless otherwise sort of stated, or it will definitely show you in the problem. Another really important number is the mass number, and the mass number is the number of protons and the number of neutrons that there is in a particular atom. So this number is important along with the atomic number, because the mass number is the number of protons plus the number of neutrons. The atomic number is the number of protons, which means if you subtract those two, protons cancel, and you will be left with the number of neutrons. So if you take the mass number minus the atomic number, it will tell you the number of neutrons there are in that particular atom. Every single element has protons, electrons, and neutrons. There is only one exception, which is our good friend hydrogen. Hydrogen has some interesting properties, and that is why on some periodic tables years ago, you actually would find hydrogen on both sides because of that. But hydrogen actually has only one proton, one electron, and it has no neutrons. Everybody else will have protons, electrons, and neutrons. And to answer your question, yes, the atomic number, which you can find on the periodic table, which again is that number up on top. This number here, which is the atomic number, which is the same thing as saying the number of protons, you could just simply go to the periodic table and see what element it is. So for example, if somebody said, what element has an atomic number of 10, you should be able to go to the periodic table and look up number 10 on top. And I don't have a periodic table in front of me, but that should hopefully say helium, I hope. Well, not helium, it should say neon there. Helium is 2. So it should say neon, or it should have the Ne symbol, and that would tell you that it is neon. You would never ever find, for example, neon with an atomic number of 7, because again, if you go to the periodic table and look up number 7, that is nitrogen. So the number of protons, which is the same thing as the atomic number, tells you exactly what element you're dealing with. You could just simply go to the periodic table and find that number, and it will tell you that. Now, when you do calculate these things, the number of protons, the number of electrons, the number of neutrons, and also the atomic number and the mass number, all these things need to be whole numbers, positive whole numbers. Can't have like a half an electron or something like that. So they all need to be whole numbers when you calculate them. So that brings me to another very common question is this number the mass number? And again, if you look on the periodic table, you will see numbers underneath the symbol. And you may say to yourself, oh, this must be the mass number then, since the top one is the atomic number. And the answer is no, it is not the mass number. That is incorrect. If the one way you could really remember that is by what it says at the very bottom. When you do the mass number, when you do the atomic number, if you calculate protons, electrons, and neutrons, they all need to be positive whole numbers. And if you look at all those numbers that are on the bottom of the periodic table, underneath each of those symbols, there's pretty much no whole numbers there. They're all decimals. And what this actually is something we'll talk about a little bit later. This is actually what is known as the atomic mass and not the mass number. What oftentimes confuses people is sometimes when you calculate the mass number, it is a number very, very close to what you find on the periodic table. And it's not that number on the bottom. So the only number here that we've been talking about that you can find on the periodic table is the atomic number. Again, the mass number is not found on the periodic table. Questions on that there? That brings us to isotopes and a couple of ways that these guys are sort of displayed. But what isotopes are really the same element, but they have a different mass. So if you remember when we were just talking about protons, electrons, and neutrons, the one thing that is the most important in terms of determining what the element is the number of protons, or the atomic number. So because these are all technically the same element, but they have different masses, the only way that could happen is if they have different numbers of neutrons. So isotopes are the same element, but they have a different mass number. And very common way that we sort of write it is like what we see down here. We write the chemical symbol. Top left goes the mass number, which is our number of protons plus our number of neutrons. bottom left goes the atomic number, which is our number of protons. An example of this would be hydrogen. Hydrogen has 1 proton and no neutrons. Deuterium, which is actually sometimes referred to as heavy hydrogen, has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. That's really the radioactive version of hydrogen. If we were to write the symbols for each of these, we have 1 proton, which is hydrogen. You would go to the periodic table and look up 1 and see H. On the bottom would go 1 for the atomic number. The mass number here would be the number of protons, which is 1, plus the number of neutrons, which is 0. So the mass number will also be 1, which would go on top. Again, mass number up on top, atomic number on the bottom. If I went to deuterium, also has 1 proton, which means its atomic number is still 1, which means if you want the symbol for that, even though it's not called hydrogen, it has 1 proton, which means it actually is hydrogen. You would go to the periodic table and find number 1. And again, atomic number bottom left. In the case of our deuterium, we have 1 proton plus 1 neutron, which gives us 2 for our mass number, which would go up on top. Now, when we get to tritium, again, although not spelled out, it's hydrogen. It has 1 proton, which means when you go to the periodic table, still going to be H for our symbol. Still going to have an atomic number of 1 on the bottom. And now our mass number is 1 plus 2, which equals 3 in this case, which would go on top. So again, if you want the number of neutrons, you take the top number minus the bottom number. So 1 minus 1 is 0. Top number here, which is 2 minus 1, which is 1. And top number here minus bottom, 3 minus 1 is 2. And again, top number minus bottom number will give you the number of neutrons, and that essentially is mass number minus atomic number. Question on that there. So again, take-home message here for this part. Atomic number found on the periodic table, number above the symbol. Every single element has its own atomic number, which is the number of protons. You could identify that element by the atomic number or the number of protons. The mass number, which is the protons and neutrons, are not found on the periodic table. You will be given enough information in these type of problems to calculate the mass number or calculate the number of neutrons as well. Any questions on that? One, just to finish up here before we call it here, another way that sometimes isotopes are written are like this, copper-64. When it's written like this number is the mass number. So that's another way. Sometimes you'll see sort of isotopes written. And again, isotopes are the same element, but different numbers of neutrons and a different mass number, and has a different mass. Any questions on any of that there? So I think this is a good place to wrap it up. Couple of reminders. I did put up a proctoral practice quiz you need to take by Friday. Again, we may use that for proctoring, so you could kind of get yourself set up to use it. It is going to be counted for completion, not necessary content on this particular one, because we may have a quiz and we may be using that to do the quiz. And speaking of quizzes, I think we will have one next Wednesday on chapter 1. So conversions, density, and that type of stuff. So I think we'll probably have one during lab sometime on Wednesday. I will update this exam schedule, but it will be during those weeks. I just haven't had a chance to pop the new one up there. I will do that. If it says you need an access code, that means you do not have the proctoral downloaded correctly or using Chrome or an extension. So that's usually why it will ask you for a code. You shouldn't need any code to take it. So again, you can find the secure proctoring thing on Canvas. It should kind of walk you through it. You do have to use Chrome and a computer with a webcam to take it. And again, if it's asking you for access code, then it's probably one of those things are not correct in that sense. It's honestly, the practice quiz is really just for, it's just for to get you understanding how to use it. So it's just a mixture of some random, pretty simple questions. There's nothing too much. And again, this particular one will be graded for completion, the proctoral practice quiz. The real quiz will be on chapter 1. It will be next week. And I think we will take it during Wednesday, during not lab time, during lecture time, either at the beginning or at the end. I'll let you know on Monday, or I'll send out an announcement when I sort of fully decide when exactly it will be. But it will be Wednesday on chapter 1. And again, I think it will probably occur during lecture time, either at the beginning or end would be my guess. And it will probably be run through Canvas type quiz. And, you know, so either we'll take the quiz and then lecture, or we'll stop early and then you can take the quiz kind of deal. No, so everybody will take it probably together during lecture time at the same time, I think. All right, any other questions on any of that stuff? Again, you need to download the extension into Chrome. You can't just use Chrome. You also have to download the proctoral extension in Chrome and use it. And again, if you have trouble, just email me and I'll try to kind of point you in the right direction, but I usually need to do that. So it's an actually extension that you have to upload into Chrome. And if you kind of click on our Canvas site where it says Secure Proctor, it will prompt you to go to their website and kind of download the extension and all that kind of stuff. Okay, we will stop here so you guys can get to the lab. Have a good day if you're out, and a nice weekend. Those that have discussion, I will see you we'll take a couple minutes or so. We'll start maybe 7:05, get a chance to stand up and stretch, and we'll have discussion again, come through the discussion. And those that have lab, have a good rest of your weekend. Make sure you type here if you did not do so.